I will give you a little bit of background, if this is working, yes, on the French management system. I'm from the management side, so I'm not in a scientific organization, but I work with scientists. And since 1964, there was a French water law which created 6 river basin agencies, which are the basins that you can see on this map, and 7 river basin committees. In France, we apply what we call the water pays for water principle, or the polluter pays principles. Basically, the river basin agencies are collecting environmental taxes from farmers, industrials, or private users. And this money is not going to the Ministry of Finance in Paris. It stays in the river basin, and it is then redistributed to finance projects to reduce pollution, restore rivers, and etc. The river basin agencies are responsible for preparing the river basin management plans according to the European directives. And we also work with scientists to improve knowledge and management. We have a budget dedicated to this. Now, to give you some description of the Rhône basin, we have an objective to reach good ecological status by 2027. This is according to the European Union Water Framework Directive. This is a very ambitious target because if you look at the hydromorphological pressures on the Rhône basin, what you will see is that about 35% of rivers have a disrupted hydrological regime. About 45% have their biological and sediment transport continuity disrupted by weirs or dams, and about half of the rivers are at risk of not reaching good ecological status because of morphological pressure. So because of channelization, the lack of riparian vegetation, and so forth. And you can see that in some areas of the basin, most rivers are in red, so with severe pressures on the morphology in this case. And when you look at the good ecological status, which is defined looking at fish, invertebrates, aquatic vegetation, physicochemistry, with reference conditions, you will see that there is a strong correspondence between the pressures on the morphology, in this case, and the bad, poor status of our rivers. Now, just one more slide to define what we mean by hydromorphological river restoration. So I take the definition of Hadis and all. Hydromorphological river restoration is the re-establishment of natural processes, that is the variation of flow, sediment movement, of features, sediment sizes and river shape, and physical habitats of a river system. And that includes submerged, bank and floodplain areas. So this is, for example, an illustration of rivers where you have a variety of morphological units with riffles, pools, bars, more or less vegetated, or riparian vegetation. This is an example of an area of a river with say, good morphological functioning. So the Rhône Mediterranean Basin Agency spends on average 90 million euros per year on river restoration projects. And we are also in the United Nations Decade of Ecosystem Restoration, which aims to prevent, halt and reverse the loss of nature. So this is something which is important for our River Basin Agency. Now, one first case study that I wanted to talk about is about making space for river. At the end of the 90s, there was a strong call from geomorphologists, from Piéguet, Bravard, Malavoie, to give space to the river because rivers which are dynamics will tend to erode their banks. This is necessary for their equilibrium. This is an example here of different platform views of the river Loup in the northeast of Lyon, in Jura Mountains. And you can see that between the 19th century with a platform view in red and today, this river has taken many different paths, but it's got today a very simplified platform view. But you would still consider that this river needs space for at least the meandering pattern to develop. If you only have the width number 1 here, you will see that in terms of habitat, it's very poor, it's very constrained. If you give the river a little bit more space, you will see alluvial bars with the vegetation. And if you give the river even more space, you will allow the river to develop its meander train. And so there was a technical guide from our river basin that was written to give freedom to the rivers. But of course, rivers need also space, not just for their erodible corridor, but also for floodplain, flood energy dissipation, for lateral connectivity, biological connectivity, for the interaction with groundwater, and so forth. So there was a technical guide released in 2016 to define, restore, and protect the space of all rivers, so including rivers with low natural lateral erosion activity. One example of river corridor restoration on the River Durance in 1997, so that was after the 1994 flood event. 4 kilometers of embankments were set back, so from 100 to 200 meters, to give more space to the river and provide flood alleviation up to the 50-year flood event. So this is what you can see on those two photos. That is in red the situation before the setting back of embankments, and this is after 20 years later, and you can see that the braided pattern of this river, which is the natural pattern, came back. And very importantly, from a management perspective, we reckon 10 million euros if we had to rebuild the embankments near the river, because they undergo less stress and pressure during floods if you set them back. So it's much less costly. Another example, this is an example of a road that was built too close to a river. We have many of them in France. And this is one road here which was set back because after quite a few flood events, we realized that it was not cost effective to keep rebuilding the bank protection. So that was set. And this is just after the road was demolished and rebuilt further away. This is a much more cost effective approach. This is a map of the subcatchments where we have managed to implement this policy. But it remains challenging because we face land planning issues, of course, and we still lack some scientific data to quantify the benefits of protecting and restoring the alluvial space for rivers in terms of sediment balance, exchange with groundwater, and the ecological benefits in the floodplain. Still, we are trying to make progress on this, working with scientists on the ecosystem services and so forth. Now, another case study. We have a requirement from the Water Framework Directive to assess the risk of hydromorphological alterations at the scale of the entire French river system network. So at the scale of 225,000 of kilometers of rivers. This is a water framework requirement. And we worked with Semagraph and Valet and all to develop a model that would be able to answer this objective. So we the model is using ecological and stressor inputs obtained from remotely sensed and observational data. From that, multi-scale descriptors were derived at different scales, so at subcatchment and ridge scale and river network scale. And then a Bayesian belief network was used to define, to assess the risk of impairment following several indicators defined in the Water Framework Directive. So we have indicators for the risk of impairment of morphology, ecological continuity, and the hydrological regime. And we used that to assess the risk, the impacts that the impairments can have on the ecology. And we also combine it with physicochemistry to then get an idea of the risk of impairments at the scale of the entire river network and the impacts on the ecology. So I will give you one example, the simplest example in the model. If you want to assess the risk of impairment of the riparian zone structures, well, the riparian zone structures is, you can see in a simplified way, it consists of the riverbank nature and the riparian zone. So the riverbank nature, if you have a road, for example, near your river, there is a good chance that this road will be protected and you will have bank protection. Or if you have urbanization, and there was a buffer of 100 meters that was taken from either side of the river, then there is a good chance that in an urbanized context, the banks will also be protected by concrete or other ripraps or so. And you will have an altered riverbank nature as opposed to natural riverbanks, which can be eroded or offer habitats to birds, for example. And if you look at the riparian vegetation, we can extract the presence of riparian vegetation in a 10 meter and 30 meter buffer. And we can combine it because we have the national database simplified, but which can be used at least for a first assessment of this. And we can combine it with altitude because, say, at 2,000 meter high, at least in France, it's normal not to have a riparian vegetation. Combining this, you can have a risk assessment of impairment of the riverbank structure. So this model was used to assess the probabilities of impairments of the riparian zone structures at the scale of France and at the scale of the river basin. What is in red here, for example, in the northern part is a very rural area where farmers tend to cut riparian vegetation, and so there is no riparian vegetation buffer. And around the Mediterranean Sea is a very urbanized area where the river banks, for example, are very artificialized. So thanks to this model, we had a probability of impairments for 10 hydromorphological parameters, which are defined in the Water Framework Directive. So it integrates multi-scale quantitative and qualitative descriptors to identify multiple pressure sources and pathways in the river network. And what was very useful for managers is that let's say 85% of the river network is made of small rivers with Strahler order 1, 2, and 3, and they are not well known. I mean, for many of those rivers, we do not have data. So this model, CERA, was used to at least provide a first assessment of pressures of those rivers. And it's been recently updated with a model now called PRIMO. Okay, third case study. We have questions about whether the biodiversity and hydromorphology objectives are achievable. When you look at synthesis, looking at many river restoration projects, you will see that you have a great variety of responses when you look at the richness or the abundance of various organism groups. Overall, the effects of hydromorphological restoration seem to be positive, but it's very variable. Why? Because you have natural variability, whether you had floods or droughts, for example. The monitoring design is often insufficient in terms of spatial and temporal coverage. The protocols can be heterogeneous. Sometimes there is a lack of context variables, and so it's very difficult to be conclusive. And so the scientists made a call to have a more structured approach to monitoring and appraisal of restoration schemes. So we followed this call with the French Office of Biodiversity to set up a demonstration sites network with scientific and operational objectives. So in the scientific objectives, there was the need to get standardized scientific data over the long term to characterize the effects of a type of restoration, and give feedback on the efficiency of river restoration. Does it work, basically? And we had operational objectives to evaluate the physical and biological responses, to be able also to communicate on the effects of an operation, and to develop ecological engineering and monitoring design adapted to each restoration project. So there was a monitoring guide, all in one, that was released for 7 hydromorphological restoration types. We apply the before-after control impact design. So this is an example of, say, a river. This part has been straightened, and the project is to have a remeandering section. You will have a monitoring station in the restored reach, but you will also have a monitoring station in a non-restored reach, straightened, and a monitoring section in an unaltered reach. You will look at the results on those stations over 10 years, so say 2-3 years before when you can, and at least 7-8 years after. And you will look at that on biology, morphology, and context data, temperature, water quality, hydromorphology, and so forth. And you will store that in institutional data bank. So we have about 20 sites on the Rhône basin. There are about 45 restoration sites in France, mostly remeandering and weir removal. And we can say that the first results are quite encouraging. This is one site that we have, southeast of Lyon. So this was before restoration. You had a concrete channel. This is after restoration. So the concrete was removed with a sediment replenishment and the vegetation allowed to come back. We gave more space to the river to also account for flood alleviation and the increase in roughness that you would get by changing the substrate. This is another site, that restoration site we had. It was actually the first restoration site that we had on the Rhone Basin in the demonstration network. So there was a gravel mining pond set up in the river, which was disrupting the ecological continuity. It was increasing also the water temperature of the river downstream. And so the solution was to build a new channel to bypass this gravel mining pond. So this is a photograph of the construction work. This is after the water was allowed to enter the channel. And this is 7 months after, 2 years after, 3 years after. You can see the vegetation developing. And after 10 years, the monitoring showed that for the first time, good ecological status was reached for both fish and invertebrates. Why so long? Because we had problem with water quality. There was a wastewater treatment plant upstream which was not working well, and so there was repair work which was carried out, and after that we were able to reach good ecological status on this. So in terms of perspectives, we still need to improve the data storage process, and we still need to analyze the monitoring data, transfer the results, and improve the understanding between the hydromorphology and the biology and the geomorphological trajectories of the restored sites. And what we've done recently is that 3 years ago we've added social monitoring. It's only on the Rhone Basin to assess the links between humans and the river. Last case, quickly, is the use of airborne thermal infrared imaging on the river basin. So it's a remote sensing tool which can have high resolution, typically 30 centimeter per pixel, with high precision of about 0.3 degrees Celsius, and we can use that on large scale. So you get the data, so the thermal images with visible images, photographs. You will calibrate the data with the local thermometer, and you will have classification looking at geomorphological units to be able to interpret the thermal data. And with that we can have map of temperature maps and profiles along the river, which can be really useful. So I will illustrate this. This has been applied in quite a few areas now on the river basin over the past 15 years, and it's really useful, for example, to be able to detect karstic outflows. This is an example on the Cèze River in the south of Lyon. In the summer, you will see the cold pockets of water, groundwater coming into the river. And in winter, you will see that as warm pockets of water. And for us, this is very precious data because it is data at risk scale as opposed to point scale data. And we use that as a marker of geomorphic dysfunctioning, for example, to see the impacts of dams or the lack of riparian vegetation or urbanization. And we can use it to see also the thermal refuge that will be used for fish or the biology. And we use that to prioritize where we can restore ecological continuity. This is one last example. This is a catchment quite urbanized in the southwest of Lyon. In the upstream part of the catchment, you have biological reservoirs which act as thermal refuge. We were able to see that. While in the downstream part, you have an urbanized area where the water is warm and it's even intermittent. Now, what we did is we restored ecological continuity by removing a lot of weirs or dams, like on this picture. So this is a 5-meter weir that was removed, or by building fishways, for example, or bypass rivers to be able to allow access to the trouts to reach the upstream areas in the summer, where it's very hot, and then to come back in the autumn. And that has been proved as a quite successful strategy for restoration. For the final conclusions, in my experience, linking science and management takes time to build a mutual understanding, scientific and operational needs. All those projects, a lot of time to develop, but they've been really useful for managers. On the Rhone Basin, we have framework agreements between scientific and management organizations. We also have a scientific advisory board, which really helps to build this mutual understanding. We still need more integrated management approaches. We've made progress on this, and we've got new knowledge and we've improved monitoring. But we need better links between hydromorphological processes and the biology. We need to improve also the prediction of geomorphological trajectories. And also we need to include social and human sciences in projects. I mean, we've started doing it and we work with social scientists, but we still need to improve this. And I thank you very much for your attention on this. The green points are all the weirs on which we restored ecological continuity. And the two in orange actually have now been removed. It's done. And even this one is done. So that means on the entire axis, we had 35 weirs, and they've all been either removed or equipped with fishways or a bypass channel. But you can see that in tributaries we still have some work. And in this area we have also genetic data for fish, and we have seen that the population were isolated before, the fish population of trouts, but following the restoration of continuity, we have seen it changed. But it's not changed in the tributaries where it's still disconnected, fragmented.
Long live India and France friendship.